Okay, I hope everyone is doing well. So just like I just started recording, like the previous sessions, please interrupt me by just unmuting yourself if you have any questions or any concerns, especially when I ask if you have any questions. Okay, so today there are a few announcements, then we will have some pop-up questions, then we will have a review of the recorded videos, hopefully almost 10 minutes with question answers if you have any questions, and then we will continue and finish chapter 3. If we have time, I will continue with the introduction for the chapter 4, but usually that's not the case, so let's not aim for the moon. Okay, so the first announcement is that the quiz 3 will be published on Monday. This will be on chapter 3, and then quiz 4 will follow it the next week. No, the week of after that is your midterm. Okay, so I will discuss the quiz 4. Probably I would integrate it with quiz the chapter 5. And you will have your midterm exam on October 29th. That's 2 weeks from now. And it will be during the class time. It is closed book. You have it is individual closed books, and you are not allowed to use internet, yours or any other have any other collaboration, etc. One page cheat sheet is allowed, and then the samples are your labs and somehow also your quizzes. For some of the more interesting ones, such as the TCP connections, etc., I basically have mentioned that these are the sample questions in your quizzes. More details, I will announce it later. I'm just assessing different options to make it better for everybody. So these are the main announcements. So the next section, hopefully, is the questions. So there are a few questions here that I'm going to show you first. So maybe you're seeing the quizzes. So just to save some time, I'm just typing A, B, or C, and then you are seeing the options on the slides. So the first choice is A, and B, C, D, and E. Okay, so I have started the first question. And you will see the question here, so please answer based on what you see on the screen for question 1. So just a few more seconds to allow the other people answer the question. Okay, so we had 20 correct answer, and the correct answer is both A and B. So when we are talking about the cumulative ACK, basically it's the receiver sends the acknowledgement for the packet with the largest sequence number it has received, and that's in order. So that's pretty important. It should be in order. If there is a gap, then it is not the largest sequence number. So because of this reason, C is not correct. Then also it indicates that the packets up to and including that sequence number are received in order. So the sender can just send another packet. Okay, so I'm going to start the second question. Again, you still see it on the slide. So question 2, A, B, C, D, and E. Okay. A, B, C, D, and E are the choices. So I've started the second question. So a few more seconds, just allowing to the other people think about it a little bit more. So this is the distribution of responses, and then the correct answer is D. So a retransmission occurs when a timeout happens or the sender receives 3 duplicate acknowledgements. So it is the sender receives the same acknowledgement with the same sequence number, basically 3 times. So one more question, and here, this is pretty important question. So please try your best to understand what is going on in this communication, in a TCP communication, and similar questions. What is the sequence number or acknowledgement? You will see it in your exams. So again, I'm just typing A, B, C, and D here. A few more seconds. Yeah, I'm just showing the answers to you. So the majority of the class have answered correctly, which is choice B. And I'm going through it in a few seconds. So this is pretty important, and you kind of have to know what is happening here. So let's look at it together. So you have the answers here, and for the slides that you have, the answers are at the end of your slides. So here what happens? Just look at the previous slide here. In TCP, retransmissions are triggered by a timeout event or a receipt of duplicate acknowledgements. So here, host A has sent something, but then the acknowledgement is lost and the timeout has occurred. So this is the retransmission of the previous one. So for sure, this sequence number is the exact same sequence number that it was sent previously. And it is pretty important to note that the sequence numbers, this is the sequence number for the first byte stream that it is sending. So it means 30 plus 1. So the expected one after that is 35. This is the acknowledgement number. So the acknowledgement shows the sequence number, the next sequence number that the receiver is expecting to receive. And because it includes the sequence number 30 that was sent first, so the next expected one is 35. And again, here this sequence number is 30, and then this acknowledgement is 35. And this kind of sequence number acknowledgement is pretty important. You will for sure have such a question in your midterm exam. I will let you talk in a few seconds. So then what happens is basically is that something else I want you to think about and to consider here is that we have discussed that these bytes can be different in each of the segments that it is sending in TCP. So this first one can be 5 bytes. If there was another message sent here, could be 10 bytes and so on and so forth until it reaches the maximum segment size. So there was a question. Please unmute yourself and ask.
Yeah, so if the ACK was received and we had a second packet sent, then the sequence number would be 35, right?
The ACK would be, yes, so the sequence number would be 35 for the next one if the ACK was received. And then, yes, 30 plus 35, yeah, this ACK would be the same as this one if the timeout didn't occur and the ACK wasn't lost.
Okay.
And then this one could be also changed. So it could be 5 bytes, it could be any other number.
Yes. Thanks.
Okay, great. So this is what we actually want you have to know. So the TCP segment structure, we have discussed about a lot of different things. So we have discussed about source port and destination numbers. The header size is 32 bits, so this is pretty important. It has a sequence number which shows the bytes of the data that is going to the byte stream. And you have seen in the handshaking protocol that both sender and receiver send some initial sequence numbers that they want to communicate to each other. And just look at the slides and also the lectures on the Tuesday for this week to note a little bit about that one when we are talking about the handshaking. Because if you think about the client-server application, the client initiates that one, but then the server also has to send some data. So they have different sequence numbers that they send to each other. And then the acknowledgement number is the sequence number of the next expected byte. So, and then how the messages, how the sender or receiver, how one host knows that this is an acknowledgement number, this bit, A bit, is turned on. So instead of 0, if A bit is turned on and it is 1, it means that this message, this whole segment, is an acknowledgement. So we have discussed also about the receiver window. This is pretty important when we discuss about the flow control. Basically, we want to restrict the fast sender and match the speed of the sender to the speed that the receiver is willing to accept. So basically, the receiver sends what is the number of bytes that I'm willing to accept, and then the sender doesn't send more than that number of bytes in a flight. So this is the receiver window. It shows with RWND, I believe. in the previous slides. Then we have also a header length because there are some different variable options here. We have a length for the header specifically. The checksum is for error checking. You should consider that. C and E are used for congestion notification. We're going to talk about it. And also these 3 bits are used for connection management. So all for those handshaking that we were discussing. And as I mentioned, this payload, the actual data, this can be sent with different lengths. So the first the first segment that the sender sends can be 5 bytes, the next one would be 10 bytes, and so on and so forth. So because this can be changed, then also you have to know, like they have to know what is the sequence number and so on and so forth. So this is pretty important. Then the other one is that, so let me see what I wanted to show you here. Okay, I think I have to write. So I'm going to disconnect my other monitor so I can write. And if it freezes, just let me know. So you should be able to see my screen and to see something. Oh, what's going on? Okay. Okay, so you should be able to see that I'm writing something here. So please let me know otherwise.
I can't see the screen.
You can't?
No.
Let me stop sharing and see what is going on. Okay. How about now?
Yep.
Good.
See it.
Okay. Okay, great. So hopefully I'm going to write something and you are able to see it. So this is pretty important that I wanted to tell you. So when we are talking about a segment, just think about it like this. So the host doesn't necessarily start with sequence number 1, right? So they connect, they have some initial number that they are going to send to the other party, that this is the sequence number that I'm going to send you. It starts with 92, for example, or with 100, for example, etc. And they are communicating this with the other party when they are handshaking. Okay, so this is something I wanted to note to you, that we have sequence number 92 8 bytes of the data. So it means that this sequence number is 92, and let's say in this segment there is 8 bytes of the data. So okay, so 1 2 3 4 5 2 3 4 5 6 7 and 8, right? So this is 92. This would be 99 that is sent, right? Because it's 8 bytes of the data. So then the receiver, when it receives all of these, it sends the acknowledgement and it says, hey, I have received everything up to here. So the next one that it is expecting is sequence number 100. So this shows that everything up to here has been received. So it sends an acknowledgement. This is a premature timeout scenario that we have discussed previously. The sender sends two packets and then it starts the timeout for the oldest one. So it starts the timeout for the packet that it has sent sooner. Then you see that here, the next packet, for example, that it is sending, the next segment has 20 bytes of the data. So again, it starts at 100, but then it is 20 bytes of the data. So the last one that it is sent, it is 119. So the acknowledgement for this one that it is receiving, it is 120, right? But then here, so the receiver sends the acknowledgements for these ones. So maybe I show with this laser point. So on the receiver sends the acknowledgement here. The first one, it says, I'm expecting this next sequence number. to be 100. So it means that everything up to 99 was received without any problem. And then the second one also sends here. But then when the timeout occurs, right, it has to retransmit the segment for which the timeout was set to. So the segment was this timer was set for the sequence that starts with 92 for this one, basically for this first sequence. Therefore, it retransmits the previous one. Host B doesn't send the acknowledgement 100 anymore. This is the meaning of the cumulative ACK. It sends because it has received everything up to here. So it just sends acknowledgement 120 because it shows that, hey, I have received everything up to here. So the sender doesn't receive this second segment anymore. So this is something I wanted you to notice about the acknowledgements, about the different sizes, and also about why the acknowledgement is 100 while this is this one. So hopefully this makes sense for everybody, but just let me know if you have questions. And you will see similar things in your assignments and also in your quizzes. The next thing I wanted to show you is that we have discussed about how the TCP connection is closed previously. So here I'm just showing you the graphs here. So the client, they have the establishment, right? We said that in the segments that you're seeing here, right? This finish is set to 1. That shows that this is for the closing. And then we have discussed that each of the client and server send a FIN message to each other one. So the client, when it closes the socket, it sends a FIN bit with some sequence number that it has decided previously, and then the server sends the acknowledgement for that one. So it turns the acknowledgement bit to 1. Then this is also this was the sequence number. So this is the X plus 1. This is the acknowledgement number for this one. So then at here, it waits for the server also to close the data. And then from other side, the server also has to close the connection. So the server also sends a FIN message to the other party, and then the other one, this one, the client sends the acknowledgement for that one, for that FIN bit that it's received from the server. And at this point, after it sends the acknowledgement for the FIN message that it has received from the server, then it also waits for some time and then it closes the connection. And then the same thing happens for the server. The server receives this FIN bit and then sends the FIN bit and receives the acknowledgement, and after that it closes the connection. So this is also what we have discussed. You see that these sequence numbers, X and sequence number Y, these are different because then this X belongs to the client, so belongs to the initial variable that client has set to send some messages to the server. This one is set by the server side for the sequences that it is sending to the client, so that the client also knows that what is the data, the sequence number of the data that it is receiving on its own side. So I think with this one, so we have discussed about these ones. Any questions so far? Okay, so let's continue our discussion with the congestion control. So we have also seen the congestion control previously. The congestion control, basically the question is, we have two different flows here between that are passing through one route, right? And then by flows is basically data flow between two hosts or a client and the server. So we wanted to know that what happens if the sender increases the rate of the data, which we show with lambda in, and then we show the throughput, how much data is received at the receiver side per some specific time. with lambda out. We show it with lambda out. So we want to know what happens if we increase lambda in, what happens to the lambda out, right? In the ideal case that there is no problem, etc., you see that as we increase the lambda in, and the lambda out also increases linearly, but then the maximum is r over 2 because it's shared among two of them. If it was 3, it would be r over 3, right? So the reason is that this is the link capacity. So it doesn't matter that how much you increase this, how much the sender increases its rate, the link can only handle r bits per second, right? So it cannot be sent, it cannot send more than that. Therefore, this is the maximum throughput that the receiver is receiving at some point. And then we have also seen in chapter 1 that this seems to be good, but then it's as it reaches to this r over 2, we will have a lot of delay that is happening because then there is a large queue that is happening on the router, and then the delay is basically it's increasing so much. So we have also discussed a more realistic version of this one, where the packets can be retransmitted because they are lost or the acknowledgements are delayed, etc. So therefore, we know that some packets are retransmitted, that we show that with lambda in, as the rate that the data that host A, that sender, is sending some data. That's the original data that is passed from the application layer to it, plus some retransmission data. But then, from the point of view of the receiver, it doesn't matter if a packet is received 3 times. From the point of view of the receiver, it's only one packet that it's received, right? It's the same packet that is retransmitted, let's say 3 times, but then the receiver only requires one version of this, like one of those packets, to complete the gaps that it has, the gap for the data that it has received. Therefore, the size that we see here, the kind of delay that we see here for lambda in, it's a little bit less than. So this part that you see is less than the ideal case. This is the diagonal, this is the ideal case, and then for lambda in prime, then this is less than that. And then finally, we have also discussed this point, that it's based on when we have multiple routers. So we have discussed a lot of reasons that what happens as the senders increase their sending rate, but then as it approaches to r over 2, the throughput for all of these receivers almost drops to 0. So this is pretty important, and this is more realistic, as you see here. So we have discussed a lot of things about this congestion and then what can happen. Now, in today's section, we want to know, how does TCP handle all of those things? So any questions?
Can you just go back to the last slide for a sec?
This one.
Yeah, okay, thanks.
No
Makes
worries.
sense.
So any questions? Okay, so we have also discussed there are generally 2 approaches for the congestion control. One is the end-to-end congestion control, that just the senders, they just infer that, hey, there is a loss happening or there's a delay happening. This is the approach that is taken by TCP. There is also a network-assisted congestion control, that the routers directly send some information to say that, hey, I'm reaching that congestion level, so decrease your rate to the sender. So we will see both approaches in today's discussion. So the first question that basically we want to answer here is that in a TCP congestion control, the first question is how to perceive congestion. So we have discussed this with 2 approaches, but we still don't know how to perceive it, both from the end systems and also the network routers. The other questions that we have to answer is that now, as a sender, I know that, hey, the system is, the network is congested. So how should I limit my sending rate? And also how to change that sending rate so whenever the network is not congested, still I can increase my sending rate. So these are the type of questions that we want to see what TCP mechanism is chooses to answer to handle these situations. So the first question, how to perceive the congestion. So what do you think? You can unmute yourself and talk. So we have a sender who wants to know if congestion has happened, right? How the sender can think about a congestion. So don't be shy, just unmute yourself and talk, although the answer is here, but then I want you to think about it and talk.
Want to slow down the rate of transmission? Like how many you're sending out?
How does the sender knows to that it should slow down? What happens that the sender can understand that it should slow down?
If it's getting too many acknowledgements.
Too many duplicate acknowledgements.
Too many duplicate triple X, I guess.
Yeah, exactly. So that is one of the points. So in question 2, when we were reviewing those pop-up questions at the start, right? You know that the sender retransmits the data even if the timeout occurs or it receives duplicate acts. So just think about it that you are the sender. Now, what do you do? So it happens multiple times that you receive some duplicate acknowledgements. So it shows that there is some problem that the network delays sending these acknowledgements, right? So it should be congested that that acknowledgement cannot receive on time. The other point is that if the timeout occurs, so there are some losses happening here. So if the loss happens, basically that means that the router queue is full. So the packet is lost or the acknowledgement is lost. It doesn't matter. Something is lost there. So the packet acknowledgement is not received at the other party. So again, sender knows that, okay, so now the router buffer is full, and then I have to slow down. So it's basically an implicit end-to-end feedback that we are discussing from the by end-to-end, it means just the host, not the network core. So anything at network edge that we are discussing, they want to find out if they receive the acknowledgement, they will speed up. If they don't receive the acknowledgements on time, then they will slow down. And this is pretty like simple approach. So this is called AIMD algorithm, and it was developed in sometime in 1980s, I believe, and that's one of the principles of TCP congestion control. So here, I want to show what does that mean. So you should see a graph here. On the x-axis, you see the time. On the y-axis, we are showing the TCP sending rate. So how it happens is that the TCP, basically the sender, sends some data, and if it receives duplicate acts or if a lost event happens, then it sends less. So it decreases its sending rate. Then it increases until a second loss happens. Then it decreases, then increases until the loss happens, and so on and so forth. So this is pretty interesting, and it's called basically it's trying to probe the bandwidth. So if you think about it, these are like, if you look at these diagram, these are somehow linear graphs that you see. So it is called additive increase, multiplicative decrease. That's AIMD algorithm that you see here. This AI is additive increase. So it basically says that the sender increases the rate by one maximum segment size, or MSS, for every RTT until a loss happens. And then if a loss happens, it just decreases in half. Like this should be half of this one. So it decreases the sending rate in half, and then it just goes back again and increases that one. So, and then this is the MD part is multiplicative decrease. So this is pretty interesting. This is a sawtooth kind of behavior that you see here. It's basically the probing the bandwidth, and you can just think about it. That's an example from the authors of the textbook, but I really like it. That it's like a kid asking the parents of how much more they want. So they ask for more until you get angry. Then they kind of back off, and then they want to try again until they see what is their limit, right? So this is exactly what is happening. It is probing the bandwidth, the sender. So it says, hey, this is the loss. I have to decrease this. Then it increases, then decreases, then increases, and then and so on and so forth. So, but let's think about the multiplicative decrease in a little bit more detail. So the sending rate is cut in half when a loss is detected by triple duplicate acknowledgement. This is called TCP Reno. So if the event is that it just receives triple duplicate acknowledgement, it cuts the sending rate in half. But if a loss occurs because of a timeout, so it is a more severe issue, this is called TCP Tahoe, and it basically cuts the sending rate to only one maximum segment size. And then by maximum segment size, just I'm just remind you again that if it was the TCP segment, right, we had some payload here, and then these are the header values. So this payload can be different, even the header can be different, but then there is a maximum size for this TCP segment. And then we call it MSS, maximum segment size. So it means that it only sends one MSS if a loss occurs. So these are some of the details. But then the question is why we don't have multiple increases, and just it is additive increases. So why this is not multiple each time? Years after the AIMD algorithm was presented, it was shown that it is basically the best property that is scalable, makes this algorithm scalable. So just think about it that this is a distributed asynchronous algorithm that all of the hosts on the internet are using it, and then it's still working. So it optimizes the congestion flow rates over the whole network, and it's kind of very scalable and stable. So these are shown by like mathematical proofs, etc., and then we don't require those things, but then this is good to know that this is pretty interesting algorithm, although it is very old. So the TCP congestion, any questions so far? Okay, so the TCP congestion control, let's look at some more details. Hopefully you remember such a diagram from selective repeat and go back in that we have discussed previously. So the sender, this is the sender sequence number space. So it means that these are the bytes that sender can send, and just think about each of them, for example, as one segment. The green ones are all the bytes that the sender has sent and also have received the acknowledgement. The yellow part is all the bytes that the sender has sent, but they still haven't received the acknowledgement. So these are just in-flight bytes that the sender has sent. And then this is the last byte that is sent. These are the blue parts are the ones that it can still send if some data is available. So if some data comes from the application layer, the sender still can send this amount of bytes, although it hasn't used it right now. And then the rest are basically not usable. So these blue and yellow parts all together, this is something that we call it congestion window, CWND. So how this works is basically these are just, again, just think about that these are all very low level implementation. So we are talking about these variables and then the numbers, etc. So that's what we have to talk about all of these, although you don't want to implement this. So the sender basically, how does it control the congestion? The sender limits its transmission to the last byte that is sent minus the last byte that it is acknowledgement. It should be some number less than or equal to the CWND, that congestion window. So this is pretty simple. The point is that this congestion window, it's a dynamic. So it's a dynamic number. So it is adjusted based on the observation in the network congestion, and then that's part of the implementation of the TCP congestion control. So when we're talking about this, it's also good to note that the TCP sending behavior and then how much is the actual rate of the TCP. So it basically means that the TCP can send equal to the congestion window. So the CWND bytes over one RTT. And then for that RTT, so it means that it just sends all of these bytes and then waits for some number of time, for some RTT time, right? So then basically you can say that the rate is CWND over RTT bytes per second. So that would be the rate of the TCP. And then if this CWND is increased, then basically the rate increases. And then if this one decreases, then the rate also decreases. So this is something that it helps on how the TCP congestion control works. So then the question is how to limit the sending rate again. We have discussed about this. Is basically limits the unacknowledgement segments in the pipeline by this number. And previously you have seen something like this, that receiver window that we have just discussed, that the receiver sends for the control flow. Basically the sender is limited by the minimum of this receiver window and then the congestion window that we have discussed right now. So this is also something that I wanted to note, and it's good to know. So we have discussed a lot about the loss event. Now let's talk about the success event. So what happens if an acknowledgement is received? So far we have discussed that, okay, what happens if an acknowledgement is delayed? Basically this triple duplicate acknowledgements or a timeout occurs. So that's a failure event. But then here, what is the success event is that when the acknowledgement is received, so then the sender hopefully can increase the congestion window size. So we want to discuss the two modes for that the TCP uses for this one. But before going that, I feel I have talked too much. So any questions?
Good.
Okay. Thank you for answering. So it's good that I have I should have some signals. So it's exactly like the same thing that we are discussing. We are discussing all the mechanisms because all of these mechanisms, because sender and receiver are not able to see the other party and they don't know the state of the other party. So you should give me some signals that it is working and you don't have any question. Okay, so in a success event, there are basically two modes for the TCP that we're discussing, the slow start and then congestion avoidance. These are pretty easy. So these are pretty intuitive. So you might find it a little bit boring, but then it's also interesting to know that these are the building blocks of the internet and then how the network, as you see today, is actually based on all of these principles. So we call it a slow start, but this is not actually a slow start. So host A sends one segment for one RTT. So this is what we are discussing. One segment, and then this is the congestion window for one RTT. If you're sending a question, please unmute yourself in the chat because I'm not able, I just had to disconnect my my other monitor in order to be able to write down here, so I'm not able to see all of your chats. I will go and check it at the end of the class, but in the middle, if you have questions, just unmute yourself. I can just hear the some voices. Okay, so this is what we have discussed. So host A wants to start sending some messages. So it just sends one segment, and initially it sets the congestion window to one maximum segment size. So it just sends one segment over one RTT. Then nothing happens, the loss or the delay doesn't happen. So then in the next RTT, so this is again this time and this time is almost the same. So in the next RTT, it sends two segments. So it doubles this congestion window per RTT until it reaches a point that the loss happens. So it doubles it, then 2 times 2 would be 4. The next time it sends 4. The next time it sends 8 until a loss event happens. And we will discuss then what that means. So basically, it is exponentially increasing the congestion window size. And basically, it means that increasing the congestion window size means that the sender is increasing its sending rate exponentially. So a slow start, it's just for this one segment that is sent, but that's not actually a very slow start. So then basically the initial rate is very slow, but it ramps up exponentially fast, the sender, so it increases the rate that it is sending. So here, then we basically want to know then what happens. So what happens that we have discussed previously, that is the difference between the triple duplicate acknowledgement and also if a loss happens. So how to connect all of these basically together, that loss event or failure and this slow start that we have discussed right now. So in this diagram, this is also, I think, a similar question to your lab 4. I think so. So this is the transmission round, right? So this is RTT, the first RTT, the second RTT, third RTT, and so on and so forth. Then on the y-axis, you see the congestion window in segments. So this means that this is the size of the congestion window is 2 segment, 4 segment, and so on and so forth. So the sender starts somewhere here. Let's say the first threshold, we just said this is a variable that we have to talk about. We have to set it in order for them to it helps the sender basically for the congestion avoidance, and we will discuss it right now. So let's say the initial threshold is 8, and then the sender first sends one segment in the first RTT. In the second RTT, loss didn't happen, so it doubles it, so it sends 2. It increases the congestion window to 2. In the third RTT, in the next one, again 2 times 2, it would be 4, and so on. So it should at the third RTT it is 2. At the fourth RTT, it should be somewhere very high here, right? So doubling 4 would be 8. It should increase to 8, but because it passes the threshold, it's just here. So this is increased to 2 times, so it would be 8. And then after this threshold, it just doesn't double it anymore. So instead of setting the congestion window to 16, it basically just linearly adds to it. So increases one by one. In the next RTT, in RTT 5, it just increases the congestion window that was 8 to 9, then to 10, and so on and so forth, until the loss occurs here. So then basically the implementation for the SS threshold is that if the loss occurs, then this threshold is set to half of this congestion window that was set previously. So it is 12 right now, it is set to 6, right? And then because it was a loss, so this one, uses the TCP Tahoe. So it goes and sets the maximum size to 1 again. So just remember that the Tahoe, when the loss occurs, it's by the timeout. So that's the worst case that can happen. Therefore, it has to decrease the congestion window to as minimum as possible. And then from there, it just goes up again until it reaches the threshold. And then after this threshold, so it exponentially increases. That's the slow start part. And then after this, it just linearly goes up. And what is this dark one? That is, let's say if this happened by a triple duplicate acknowledgement, not a loss. So it would just set the congestion window and the threshold to half the windows, to half the congestion window size, and then it will increase it linearly from there. So this is pretty simple, and I hope that it is not very confusing. But this is also one of the questions that you have in your lab. So that's the meaning, and that's what you should do basically. So this increasing linearly that you see after the threshold here, here, and here, this is called congestion avoidance. So so it means that it should start very slowly and then exponentially increases, but then it increases the congestion window to some point, and after that some point, that is basically this threshold that we have here, it just increases linearly, so it tries to avoid the congestion as much as possible. So these are only some more details. So there is a TCP congestion control that you're seeing here. I want you to just go through it yourself. Everything that we have discussed so far is here. What is the slow start? What is the congestion control? And that fast recovery to coming back from the congestion control. So the other part is basically all the discussions that we have seen so far. This is the summary for the TCP congestion control. If a triple duplicate ACK occurs, the threshold is set to half the congestion window. The congestion window is set to the threshold. That's the black line that we have seen. And then if a timeout occurs, then the threshold is set to half of the congestion window, but then the congestion window is set to 1. So that is the worst case that can happen. So now I show you the graph right now that I have discussed a lot. I want you to draw the same graph. So the congestion window changes versus RTT for a case where the initial threshold is 5, then a duplicate ACK is received at RTT 7, and then a loss occurs at RTT 11. So you have 5 minutes. Please work on it individually, and then we will continue our discussions. And in the meantime, I'm also going to check the questions. I've extended the lab for due date to 1 more week. So it was due to this week. I think I've extended to 23rd. So I just discussed about lab for due date, and I have made that announcement previously, but just for some people who have lost it, lab for, because this week was a Thanksgiving, and then some students requested to have more time. I just extended lab for to October 23rd, so end of next week. So one more minute for the for the graph, and then I will continue the lecture.
I have a
So-
question about the
Yeah,
graph.
go ahead.
So the initial SS thresh, shouldn't it be like 4 or 8 or some multiple of 2? If it's coming from slow start, or it's not coming from slow start.
So I think this is your question. So if it's coming from a slow start, then it is doubled at each RTT.
So then the initial SS thresh, like I don't get how we would get 5 if we're using slow start. Wouldn't it
Oh, you don't get 5. I'm just asking you to go over time. So basically what I'm asking you is that you go over time. Okay. So basically what I'm asking you is that just think about that this is the sender. It's still sending sometime. So I just put the previous graph here. So this is the left one is not the actual answer. I just set it here for your reference. So if this is RTTP, RTT, and then this is the congestion window size. So the initial threshold is set to 5. Let's say this is 5, then 4, 3, 2, and 1. Okay. So it starts at RTT1, it sends 1 segment, then at the RTT2, it doubles it, it sends 2 segments. At RTT3, it sends 4 segments. Right, so this would be 4 segments. And this is the threshold that it is sending. So maybe I should use something else here. Okay, so I'm showing the actual graph here. Yes.
So we're into congestion avoidance at 4.
So here, 4 times 2, it should go to 8, but then it actually doesn't reach that. So at 4, what did I mention here? So this is the duplicate jack is received at 7. So yes, so if this is the threshold, it should go at 8, but it actually doesn't go at 8. So how does it work then? So I think it's increased by 1, right? At 4, then 5, 6, and 7. So then here, 6, 7, 8. So it's just increased linearly after this.
Okay.
Right, 1, 2, 3.
I thought that the definition of the slow start threshold was when the slow start converted to congestion avoidance.
I didn't get what you said.
So like the slow start threshold, I thought that the definition of what a slow start threshold is when it converts from slow start to congestion avoidance. Like
Oh no, the slow is basically it just starts and then it doubles it until
the threshold is reached. Is that
until it reaches the threshold. That's a good point.
so? Yeah, I'm just kind of curious, like
So
where
until the
defined, like how does the TCP network know, like, hey, it's time. This is where the threshold should be.
So that's a good question. How initially that threshold is set. That's basically your question.
Yeah.
Take a look at it again. I don't know. I will get back to you. That's a good point.
Okay.
So, yeah. Because in the definition of a slow start, it basically increases exponentially, like it's doubled until it reaches a loss. But this is not what happens actually. It just goes to the threshold, and then after the threshold, it just goes linearly. So instead of doubling at each point. So I don't know how this first threshold is set initially. I assume it's based on some heuristics that are happening in the network. But I don't know how this is implemented in TCP. I will take a look at it and let you know.
Okay, cool.
Okay, so basically you get it. This is what actually I want from you. So here, then the duplicate ACK occurs. So instead of coming down to 1, it just makes it in half. And then, so 1, 2, 3. So makes it in half. So it reaches at 4. And then it starts again linearly from here. And then this will be your new threshold. Okay, so sorry about the very bad drawing. Yeah, but this is something I want just to go through it. Okay, so so these are optional. These are not mentioned in the 7th edition. So these are kind of new things that are added in the 8th edition, but these are good to know. So basically, there is a better version of AIMD to probe the bandwidth that is called the TCP cubic, and it was used until I think very recently, or at least a couple of years ago. So the idea is that if at W max the loss occurs, so instead of reaching here slowly at a linear time, it reaches sooner when it is not at that rate, right? And then as it goes closer toward that rate that the congestion or the loss happens, then it slows down a little bit. So it's like a big highway. So you first you're driving with, I don't know, 100 kilometers per hour, and you see a congestion in front of you, a few kilometers in front of you, then you slow down. So here you speed up and then you slow down. That's the meaning of the TCP cubic. So the other point is that these are still optional, so I just put optional here. The TCP and then the congestion bottle, the TCP basically, in the TCP, the idea is that there is a specific other algorithm that is based on the delayed delayed TCP algorithm, basically, that works based on the delays. So it says that the congestion basically happens because usually there is a bottleneck here. So all of these routers are working perfect, but then this router is pretty full. So this is kind of considered as the bottleneck of my network. And then a lot of, if the sender send too much packets, then what happens is that here it gets congested basically, and then it overflows. So it doesn't matter if this source sending at a higher rate, it knows that if it sends more, then ultimately it will fool this packet, and then it will overflow this buffer, and then it will overflow. So the goal here in this kind of bottleneck approach is that just keep the end-to-end pipeline full. Like try to send as many packets as possible, but not so many that it actually fools out the bottleneck buffer. So this is the idea behind the delayed-based TCP congestion control. So it basically says, hey, I know what is the throughput that I have, because it can measure it, right? So it knows what is the number of bytes that is sent in the last RTT interval. It knows it can measure the RTT as well. So it knows this measured RTT. It also have previously observed the RTT, so it can know what is the minimum RTT that it was previously observed. So it increases this congestion control. If the measured throughput, which is this one, is very close to the uncongested throughput, then it increases linearly. Otherwise, it just decreases the congestion window. So it tries to send more packets to kind of fill this buffer, but not too much that the losses occur. So this is the idea behind the delay-based TCP. And then the good point, the point is that like that cubic and then the other ones, have been replaced by, for example, another specific congestion control algorithm, which is the TCP congestion control, that is called BBPR, and then it's used in Google's data centers and YouTube, etc. So these are good to know, kind of that like these are the basic concepts that we are discussing, and then how these are used in practice at the moment. So until this point, it was optional. This one is not optional onward. So we have discussed the approaches to control the congestion The first one was end-to-end. So in anything that we have discussed so far, just the sender infers what has happened to the packets that it's sending by receiving duplicate, acts, or loss. There is a specific congestion control that is called explicit congestion notification, or ECN. So that's basically an implementation that the core of the network, so these are the network cores, they assist in controlling the congestion. So how does it work? It basically in the IP datagram in the network layer that we will see, that we will discuss in the next chapter. Basically, in the IP datagram, there is one specific field that is called ECN. So this bit is important. So when the network is congested, the router, the packet is coming from source to the right one, the right host in the that is called the destination. So the packet arrives at this router. There is no congestion, so the ECN is still 10. It is sent to the next packet. This is a bottleneck packet. So here, this router is getting congested. So it knows that what is happening at its own links. So it sets this bit to 1. So it sends ECN as 1 to 1 and 1, and then sends it to the destination. So then this destination, when it's sending an acknowledgement, it is also turning BCE to 1. So that is 2 bits that we have seen in the TCP segment. So while it is acknowledging the packet that it has received, also it sets the ECE to 1. So now the sender knows that there are some problems that are happening in the routers and then in the network core. So it decreases its sending rate. And it happens before the congestion has actually occurred. So this is called the ECN. So it involves both IP and TCP. So it is basically the help of the two layers. And just remember that these routers, they have only these 3 layers. They don't have the top 2 layers. So the last point that I want to discuss with you about TCP is the fairness of the TCP. So let's discuss what is the fairness first. So when we call about the fairness, the goal is that if you have a bottleneck router here that has capacity R, and then there are K connections to this bottleneck router, each of these connections can send at least R over K rate over this link. So it is not the case that one of them uses almost all the bandwidth, the other one has almost none from this bandwidth. So this is the idea between TCP fairness. And then, so the question is, with everything that we have discussed so far, and then AIMD, etc., is TCP considered as a fair protocol or not? Can it provide the fairness? The answer is yes, and we will see how. So assume that the link bandwidth is R, and assume that we only have 2 connections here. So 2 hosts are using the same link. So that's why we showed it in 2D. So this is the connection throughput, the throughput for the first connection. This is the y-axis is the throughput for the second connection. So if they are using equal, then basically it means that they are using equal bandwidth. So the throughput should be closer to this line, which is 45 degrees here. So let's assume that this is not the case. So the first one uses more throughput. So this red line, it uses more throughput compared to the other one. So both of them increase their congestion window until they pass this R, and then a loss happens. So when a loss happens, they have to decrease their window by a factor of 2. So they decrease it. So then the throughput for both of them would be a little bit smaller. Then again, then they increase it and they decrease it and so on, until basically what happens is that both of them, they reach this kind of this fairness, this equal bandwidth share. So that is the convergence point, that is happening at when multiple of them are using, multiple connections are using the same link. So then the TCP is considered as a fair congestion control algorithm and a fair protocol. And because basically what happens is that they kind of based on those additive increase, multiplicative decrease, they merge to this equal bandwidth share. But there are also some other points that we have to discuss. So the first one is that we have discussed about UDP, right? So the UDP, if you remember, we usually send audio and video with UDP. They use a constant rate, but they also tolerate the packet loss. So if somebody wants a reliable data transfer, they can use the UDP protocol to use the internet, like in the transport layer. But then they can provide reliability at the application layer. This is what we have discussed previously. We have seen that the TCP has this congestion control. So it kind of limits the senders not to sending at a higher rate, because it's thinking about the whole network. But then the UDP doesn't have such a mechanism. So it is possible that an application uses UDP and then provides the reliability over the UDP if they require, but then because they don't have the congestion control mechanism at UDP, then it basically uses the whole bandwidth. So there is no such thing called internet police, etc. But then in practice, there's not much cheating happening, and it's kind of fair in this sense. And then the other fairness that you might want to think about is that we have discussed about the parallel TCP connections in chapter 2. So over one TCP request and one TCP connection, the client and server can have multiple parallel connections to send some data more. So basically it means that if a client then uses parallel connections, then they are using more bandwidth, although they're only using one connection. So then the question is it really fair or not? And that's some of the questions that you might want to think about a little bit more. Okay, so to summarize, like we have discussed a lot about the transport protocol services. Right now, you know what is multiplexing, demultiplexing. We have developed some protocols together that we called it RDT, Reliable Data Transfer. By making our channel, just think about our channel as a desirable channel, and then we made it more realistic, a channel that can have errors, a channel that can lose the packets. And we have discussed about the flow control and congestion control, and we basically have seen how we use all of those concepts in UDP and TCP. So in the next chapter, we will leave the network edge, so the application layer and transport layer that we have seen so far, and then we will go into the network core. So you will see a lot about when we are talking about IP, then what is IP, how the IP is translated to different addresses, the network addresses. Then you will have some understandings about like why you and your friend, for example, at their home, like both of you can have, for example, the same IP address, etc., and how these are controlled. So these are pretty important stuff. Some of them is really boring for some students, although they are very interesting. And then it is too much. So the network layer, we will discuss it in data plane and control plane. Each of them are one chapter, chapter 4 and chapter 5 of your textbook, and then we will continue it next. So your midterm, there are also some additional slides that if you want to remember, you can refer to those ones. So I think we are done. So the question, there is just one point that I wanted to say, and that is if you have like the midterm is up to the end of what we have discussed today, including lab 4, that I will post the solutions. Like I should actually decide about that until next week. Okay, so any questions? So thank you everyone, and have a good weekend also.